So this is Reigate College Maths Year 2, and we're covering using second derivatives. I'm just going to look at two graphs first of all, and we're going to look at them in Desmos, which is a really useful tool for doing some graphing. So let's start off by looking at reminding ourselves of what we've done before. So I've got the graph y equals x cubed minus 3x here. We can see that it starts down in the bottom left, ends up top right, like all positive cubics. And we can see that it's got two turning points. So turning points, this one is a local maximum, this one is a local minimum, are where the gradient of the curve is equal to 0. So the gradient of curve is equal to 0, also called stationary points, and we can differentiate, find find the value of x for the derivative being 0, and then we can work out that point. If you look at the way the curve turns, it's turning, if we were starting and looking along it, it's turning from left to right, it's going around a right hand. At this point here, it stops turning that way and it starts turning the other way. This point here is called a point of inflection, and we'll see in a minute that points of inflection are where our second derivative, d2y by dx squared, is equal to 0. Let's just turn that off and have a look at y equals x cubed. Now y equals x cubed doesn't have a maximum or a minimum, but it does have a point where the gradient is equal to 0. So if we differentiate, we'll do this in a moment, we'll see that at the point 0, 0, the gradient is 0, but it is not a maximum or a minimum. It is a point of inflection, that's where it starts turning. So here, turning left to right, is where the graph is concave, and here it's convex. And it's the second derivative that tells us which is which. So let's actually look at that in a little bit more detail. Okay, so here's my y equals x cubed. Let's differentiate it. So we get dy by dx is equal to 3x squared. So to find the stationary points, we're going to make the derivative equal to 0. So 3x squared equals 0 gives us x is equal to 0. The second derivative, d2y by dx squared, is equal to 6x. At x equals 0, d2y by dx squared is equal to 0 also. Now that doesn't tell us anything. So this point could now be a maximum, a minimum, or a point of inflection. In fact, it's a point of inflection, a stationary point of inflection. The point 0, 0 is a stationary point of inflection. Okay. Point of inflection is where the second derivative is equal to 0. This section of the curve is concave, this section of the curve is convex, and it's at the point of inflection that changes. So you can see x negative here, then my second derivative is going to be negative, less than 0. That's where the curve is concave. Over here, x greater than 0. Second derivative is greater than 0, it's convex. Let's just see how that works with the other graph that I showed you, which is y equals x cubed minus 3x. So dy by dx is equal to 3x squared minus 3. Let's just find the second derivative as well, d2y by dx squared That's equal to 6x. So dy by dx equals 0 gives us 3x squared minus 3 equals 0. So x squared minus 1 equals 0. So x is equal to plus or minus 1. So we can see that that's this point and this point. At x equals 1, d2y by dx squared is equal to 6. Positive tells us that this is a minimum. We can see it from the graph. Positive, so minimum. X equals minus 1, it's negative, so it's a maximum. Now, we can also see that exactly the same as y equals x cubed, when x is negative, the second derivative is going to be negative, and that means the graph is concave in the same area. So again, it's concave and convex. Concave and convex are quite tricky to remember, so it's helpful, I think, to keep in mind cubic graphs like this. In particular, y equals x cubed is a very straightforward one to remember, and if you can picture that and remember that concave and convex come in alphabetical order, so the C here is before the V here, then you can remember that that's the order going from negative to positive. So let's go and look at our course workbook now. The course workbook gives us our definition of concave is where the second derivative of the function, so it's written in function notation here, f double dashed of x is less than or equal to 0. Convex if f double dashed of x is greater than or equal to 0. Point of inflection is the point at which f double dashed of x changes sign. So at one point, one side of it it's negative, on one side of it it's positive. So let's just show here that let's look at question 1. The curve C has this equation. Show that C is concave on this interval and convex on the interval 1 to 3. So we're going to differentiate. So for A, dy by dx is equal to 3x squared minus 4x minus 4, and d2y by dx squared is equal to 6x minus 4. So then if we look at the ends of these intervals, so at x equals minus 2, d2y by dx squared is equal to, put minus 2 in there, we get minus 12 minus 16. At x equals 0, d2y by dx squared is equal to minus 4. Because this is linear and negative at both endpoints, so the function, so C is concave on the interval minus 2, 0. In fact, it's concave for a lot more than that. on the interval 1, 3, so at x equals 1, d2y by dx squared equals 2, and at x equals 3, d2y by dx squared equals 14. So C is convex on 1, 3. That's true because this is linear. So it's a straight line function, and it's positive on both ends. It must be positive everywhere. So let's look at part B. Find the coordinates of the point of inflection. B. Find x, where d2y by dx squared is equal to 0. Well, that means 6x minus 4 equals 0. So x is equal to 2 over 3. So that's the x value at this point of inflection. We need the coordinates. So at x equals 2 over 3. We're going to substitute back into our original equation. Substitute 2/3 in there. You can do that on your calculator, or you can do it manually, and we get y is equal to 47 over 27. So 2/3 47 over 27 is the point of inflection. So that's our first question. Let's now have a look at the second question. So I've got that here. Find the range of values for which the function y equals e to the x times x minus 1 is concave, and the range of values for which it's convex. So we need to find dy by dx first of all. We're going to need to use the product rule here. So I'm going to say, let's first of all differentiate e to the x, multiply by x minus 1. Differentiate e to the x, we just get e to the x, x minus 1, plus e to the x times differentiate x minus 1, so that's just 1. So this is equal to e to the x times x minus e to the x plus e to the x, so it's just x e to the x. We want the second derivative as well, d2y by dx squared is equal to, well, we've got to use the product rule on this, so this is going to be, let's differentiate x, so that's 1 times e to the x plus x times differentiate e to the x is e to the x, so that's just e to the x times x plus 1. Now, let's start off by finding the point of inflection, and then we'll find where it's convex. So we want d2y by dx squared to equal 0. So that means e to the x, x plus 1 is equal to 0. Now e to the x is always positive, so that can't be 0, so that means x plus 1 is 0, so x is equal to minus 1. Let's also find the y coordinate here. So y is equal to, let's put minus 1 into here, so we get e to the minus 1 times minus 1, which is minus 2 e to the minus 1, or minus 2 over e. So point of inflection is minus 1 minus 2 over e. Now let's just have a look at concave. We want d2y by dx squared to be less than or equal to 0. Well, that means that we've got e to the x plus 1 is less than or equal to 0. Well, we've seen from here it's exactly the same argument. That means x is less than or equal to minus 1. So that's the range of values for which the function is concave. Convex, we're going to have e to the x times x plus 1 greater than or equal to 0, and that gives us x is greater than or equal to minus 1. So we could summarize by saying concave interval is x is less than or equal to minus 1. Convex interval x is greater than or equal to minus 1. And we've finished that question. Just a quick note on the less than or equal to. What we've done here is we've followed the textbook we use, which defines concave and convex using or equal to rather than strict inequalities. You might say that this means that at x equals minus 1 the curve is both concave and convex, and that does feel a bit odd. So another way to define concave and convex is with strict inequalities, to say it's concave for the second derivative is less than 0, convex for the second derivative is greater than 0, and point of inflection is where it's equal to 0. And I'm going to finish there.